Yeah. Circuits.
All right. So before we start, couple of announcements, and I have already mentioned this in the last lecture, but your labs will be starting on September 6th. So that's the Wednesday. Now, there will be no labs in the first 2 weeks. So we are starting the semester on a Wednesday, and we'll be starting the first lab 2 weeks after the first lecture, so that you get enough time to prepare for the labs and also order the parts. And that is very important because some of the parts might take a little bit of time to get shipped. So please be proactive and order your parts as soon as possible. I see in the GroupMe chat that many of you have already started ordering the parts, but please do so if you haven't done that already. Okay. And also please note the lab venue will be MAEB, room number 226. Okay, so I had a couple of questions on this as well. So I just wanted to reiterate that. And the schedule for the lab is also mentioned here. Yes, questions? It will be the next Tuesday, yes. So the question is, since you are starting on a Wednesday, but if you're on a Monday schedule or if your schedule is on a Tuesday, so that will be the week after that, right? So we start on a Wednesday, we'll end on a Tuesday. So if your lab slot is on a Tuesday, that's the last day in that week for the lab schedule, okay? Also, what we will be having for each of these labs is also mentioned here. And as you see that lab 1 is basic introduction, Thevenin's theorem, Norton's theorems, etc., which you already know from your previous courses, and we'll also be covering some of them in today's class as well as in the first homework, so that you are well prepared for lab 1 even before it starts. And on that, I have also uploaded homework number 1, which will be due next week on a Friday. But then again, homework 1 is very basics, and we have just asked a few questions on Thevenin's theorem, Norton's theorem, voltage division, current division, and so on. So we'll be discussing all of those again in today's lecture, as well as in the next few lectures, so that you are well prepared to solve the homework problems as well. Okay. But please note that the due date is next Friday before the class starts. In terms of the labs, I'll start uploading the handouts or the lab manual starting this weekend, so that again you have a little bit of time before your lab 1, and we'll be doing the same for the other labs as well. Any questions on this, on the schedules or on the labs, homeworks? All right. And I'm also recording this class. I'll be uploading the class videos for every lecture on Canvas. It will most likely be a YouTube link. I'll upload it in YouTube and then post the link on Canvas, because I don't want to create a lot of videos on Canvas, but you'll get all the videos. That's what I just wanted to say. All right. And if you have noticed, I've also posted some of Dr. Fox's lecture videos from previous semesters. This will give you a good introduction of how this course used to be in the past, what we used to discuss, and what are the differences as compared to the previous semesters with what we are going to discuss in this particular semester. Okay, so coming back to what we started last week was on circuit analysis for electronics. And we started with pretty much fundamental. So for example, we discussed Ohm's law, we discussed KCL as well as KVL. So Kirchhoff's current laws and Kirchhoff's voltage laws. And we looked at voltage division example that, okay, if you have a input voltage source Vin or Vi, and if you have two resistances in series, the resistances add up when they are put in series. So basically the current that will be flowing through this particular loop will be the voltage divided by Ra plus Rb. So a combination of those two resistances. And if you are asked to find out what is the voltage drop across Rb or what is the voltage drop across Ra, we can also do that, because voltage drop is again current multiplied with resistance. That's something you know from Ohm's law. So as you know what is the overall current in this loop, you can just multiply that with the respective resistances to get the voltage drop across those resistances. So if you are looking for the voltage drop across Rb, that would be proportional to Rb. If you are looking for the voltage drop across Ra, that will be proportional to Ra. So whichever resistance you're looking at, the voltage drop across that will be proportional to the value of that resistance. If the resistance is high, the voltage drop will also be high. Yeah, and that's true for these kind of series resistances and the voltage division across those resistances. Similarly, we also looked into current division. And in case of current division, it's exactly the opposite, because you know that the parallel combination of two resistances, RA and RB, that can be denoted with this symbol, RA in parallel with RB. And as you already know from your basic electrical theory, is that the value of RA parallel RB will be RA multiplied with RB divided by RA plus RB. So that's your equation for two parallel resistances. Now, because that's the total amount of resistance, the equivalent resistance that you see, the equivalent voltage developed across these resistances will be the current multiplied with RA parallel RB. So if you have a current source, so remember in the previous case we had a voltage source and we looked at voltage division. Here we have a current source and we are looking at the current division between the two resistances. We already know what the equivalent resistance will be, and the current multiplied with that equivalent resistance will be the voltage drop across these resistances. Now remember, when you have these parallel resistances, the voltage drop across RA will be equal to the voltage drop across RB. Again, why? Because these nodes are common. The top terminal of RA is connected to the top terminal of RB. The bottom terminal of RA is connected to the bottom terminal of RB. So because these are same terminals, you'll have the same voltage developed across those. Right? You cannot have different voltages developed across the same terminals. Right? So the voltage drop will be same across RA and RB, but the currents will be different. How much would be the current? So for example, the current through current through the resistance RB, and let's denote that as IB. That would be the input current multiplied with RA divided by RA plus RB. So as you see that the current in a branch is proportional to the resistance of the opposite branch. In case of voltage division, it was proportional to the same resistance. Here it's proportional to the resistance in the opposite branch. And why is that? Because you already know that the voltage across these two terminals, the voltage drop across these two terminals will be input current multiplied with RA/RB divided by RA plus RB, right? Now, if you want to find out what is the individual current through RB, you have the voltage as I in multiplied with this RA times RB divided by RA plus RB. To find out what is the individual current through RB, what would you do? You'll divide this voltage by RB, right? So again, Ohm's law, voltage divided by current, divided by resistance gives you the current. So the overall voltage was input current, that's this one, multiplied with the overall equivalent resistance, which is RA times RB divided by RA plus RB. You divide everything with RB. That's how you get the current through RB. So if you do that, this RB and this RB will get cancelled, and you end up with this equation that is mentioned here. So the current through IB will be proportional to RA. That's something you need to always keep in mind. We also looked into amplifiers and the overall gain of amplifiers when, let's say, multiple amplifiers are cascaded. And why this is important, we'll see this in today's lecture, where we'll be looking at a few examples. So what we mentioned in the last lecture is that if you have, let's say, 3 amplifiers connected back to back, and this is called a cascade of stages. So it's same as like the cascades that you see in a river, that one after another. That's why it's called cascaded stages. So if you have A1, A2, and A3 as 3 amplifiers, the overall gain will be A1 multiplied with A2 multiplied with A3. And that's what we represented in terms of equations again in the last lecture. All right. Now, in today's lecture, we'll be looking at a few examples of what we had seen before, the voltage division, current division, and how to calculate the overall gain in amplifiers as well as attenuators. So that's something we'll take a look at in today's lecture. And if you look into homework 1 will involve problems related to these concepts. So let's take a look at an example first. And because we started with voltage gain, and voltage gain is easier to sort of visualize, we'll start with that kind of an example. So let's say you have a voltage source Vs, and you have this kind of a resistive network. You have R1, then in parallel you have R2 to ground, Again, in series, you have R3, and in parallel, you have R4 to ground. Okay. Now, and I mentioned parallel because from this point, it's connected to ground. But in reality, you can also see that this R3 and R4, they form a series branch together. So we look into this kind of a problem and how to solve these problems quickly, and how to sort of look into the voltages and currents at different nodes or different branches, so that just by inspection, you should be able to say what is the voltage gain in this particular circuit. So what you need to find out, you need to find out the voltage gain. And that voltage gain will be V naught over Vs. Now keep in mind that we are talking about voltage gain here, but in reality, you will actually have a voltage reduction, right? Because you cannot create more voltage than what is present at Vs. So your V naught will always be lower than Vs, which means that your gain will be lower than 1, which means that you will have a loss. That's another way of saying that it's a voltage loss, but we are just saying that your voltage gain is less than 1. That's what we'll eventually find out. Okay. So keep that in mind, that you because there are no amplifiers over here, you will eventually get a voltage loss. So your voltage gain will be less than 1. Questions?
Is gain always a positive value?
It depends the way you define it. So for example, if you think about gain and loss, then you define it gain as a positive value or something which is higher than 1. So think about the stock market. Only if you have a profit, then you'll say you have some amount of gain. Otherwise, you'll say you have loss, right? So here also it's the same thing. If your voltage, output voltage is more than the input voltage, you say you have a gain. If it is less, you'll say you have loss. Now, of course, since this is a resistive network without any kind of amplification, you'll have some amount of loss. That's what I'm telling here. But loss is also, I mean, you can represent it as a gain which is less than 1. So it's really about the way you comprehend gain and loss. If you say I have a gain which is less than 1, that means that you have a loss. All right. So how we are going to go about this problem is that we already learned about voltage division and current divisions, right? In this case, we'll be using the theories that we have learned in terms of voltage division. And then we'll try to find out what would be the equivalent voltage gain. Okay. And so what are we going to do first is that we'll first take a look at what is the equivalent resistance looking at this point. The equivalent resistance looking at this point is a series combination of R3 and R4, right? Because if you think that, okay, I have a voltage source at this point, the current will directly flow through R3 and then through R4 and to ground. So R3 and R4 are in series. So at this point, looking into this point, looking towards right, you have a total resistance of R3 plus R4. So in the next figure, we're just representing that you have R1, you have R2 to ground, and then you have R3 plus R4 to ground. So it's just an equivalent way of saying I have this R3 in series and then another R4 to ground. Okay, so this equivalence is clear. There's no doubt about this one. Now, next step, we'll be trying to look at what is the effective resistance looking at this point toward the right hand side. So you start with this figure that you have R1, then you have R2 to ground, and then you have R3 plus R4 to ground. So at this point, you'll see that you have R2 in parallel with R3 plus R4, right? So that's your equivalent resistance looking towards right-hand side at this point. Correct? So you just write that down, that you have R2 in parallel with R3 plus R4, and then you represent that with one single resistance. So you have now you have R1, which is the first resistance after the source, and then you have R2 in parallel with R3 plus R4. That resistance, this resistance of R2 in parallel with R3 plus R4, that combines all three resistances R2, R3, and R4. Now, as you see that even if you start from the first figure, you directly can write this equation down, that you have your R2, but in parallel you have R3 plus R4. Okay. All right. So now that we have established an equivalent resistance or equivalent simplified circuit, which contains your source resistance R1 and then a combination of these resistances, we'll try to look at what is the voltage gain. Now, what's the voltage gain you were asked to find? That was V naught divided by Vs. that's your voltage gain, or that's your transfer function. So you asked about whether we call it gain or loss, right? Another way of representing it is the transfer function, that how much voltage is transferred from this input side to the output. So all these terms are used equivalently when you think about electronic circuits. Someone might call it gain, someone might call it loss, someone might call it transfer function. But everything is same eventually. You want to find out how much voltage is transferred from your input to the output. All right. So now you want to find out the ratio of V0 divided by Vs. But if you look into this equivalent circuit, you do not have access to V0 anymore, because V0 was this middle node between R3 and R4. If you think about this equivalent circuit, that's hidden somewhere inside this equivalent large resistance of R2 in parallel with R3 plus R4, right? You do not have access to this node anymore in this particular circuit. What do you have access to? You have access to this node, which is Vy. So Vy is here in the original circuit. So what you can do is that you can start by looking into what is your Vy over Vs. So your Vy over Vs, that's something you can readily find out, because this is voltage division between two resistances, right? Now it becomes very easy. You already know what is the voltage division between two resistances. It's Vy is the voltage developed across this large resistance. So Vy over Vs would be this combination of resistances, R2 in parallel with R3 plus R4, divided by R2 in parallel with R3 plus R4 plus R1. So this is same as RB divided by RB plus R1, when RB is basically your combination of these resistances, right? So this is same as the voltage division theory that we learned in the previous lecture. Okay, so now you have Vy over Vs. We still don't have V0 over Vs. How to find that out? To do that, we'll assume that, okay, you started with this particular network, right? Now we know what is the value of Vy. We already know what is Vy over Vs. So we can say that Vy is Vs multiplied with this combination of all the resistances, right? So you already know what would be my Vy, right? So if you know what would be your Vy, and you know what is connected on the right-hand side of it. On the right-hand side of it, you have R3 and then R4. You can find out what is V0 over Vy, right? So V0 is this point, the final point or the final terminal where you wanted to find out the voltage. And you have an intermediate point, Vy. And you can write down the voltage division between V0 and Vy. So V0 over Vy will be R4 divided by R3 plus R4. So now we can represent V0 as a function of Vy. And initially we had represented Vy as a function of Vs and all these resistances. So from these two equations, so this is your equation number 1, and this is your equation number 2. So from these two equations, you can write down what is your V0 over Vs, right? And that's what we'll be doing in the last step. So you have your Vy over Vs, you have your V0 over Vy, your overall voltage gain, and let's call this AV. So why A? Usually when we haven't yet started discussing about amplifiers, but we generally talk about gain in terms of amplifiers, right? Whenever you have an amplifier, we say that, okay, this amplifier has a gain of 10 or a gain of 50. So to represent that you have some kind of an amplification, you say that you have this term called A, right? So whenever you will see any kind of gain term, you'll see that most of the times it will be represented with this letter A. And that basically says that you are most likely having an amplifier, and that amplifier has a gain of A. In this case, you do not have an amplifier, but because we are talking about gains, we'll still represent it as the letter A. Now, what kind of gain it is? It is a voltage gain. So the subscript V represents that this is a voltage gain. What is the voltage gain? The overall voltage gain is the output voltage divided by the input voltage, right? So gain, loss, transfer function, everything is same here. Your output divided by input. Output was V0, input was Vs. The ratio of those two is equal to Vy over Vs multiplied with V0 over Vy. So in that case, your Vy and Vy will get cancelled and you'll be left with V naught over Vs. Now individually, you know what is Vy over Vs and what is your V naught over Vy. So you can write down your overall voltage gain, which will be this. So if you look into your homework 1, you'll see that many of these problems will be like this. So for example, this is your homework 1, and you are asked to find out what is the voltage gain or what is the current gain. And you see for the first problem, you are asked to find out what is V naught over Vs. And you can use the same concepts that we learned just now to find out what is my V naught over Vs. Similarly for problem number 2 and so on. Problem number 3 is the current gain. So you needed to find out I naught over Is, and we'll look into that type of problems as well. So we look at an example. We'll look at an example which finds out the current gain of a particular circuit. But already from this example, which we just looked at right now, you can probably solve problem number 1 and problem number 2. Okay. And there are more practice examples here in this notes, which I have uploaded in your Canvas. So just look into that as well before you start solving the homework. All right, coming back to today's lecture. So now we know that how you can use the theory of voltage gain to find out the, let's say, the overall transfer function of this kind of a complex circuit. And it can be even more complex. There could be 5 more resistances connected toward right-hand side. Still, you can apply the same formula and same theory to find out the transfer function. All right. Now this is what we found out in the previous slide. If you are going to use calculators, then you can probably simplify this even more. So let's say here you have the R2 resistance here. The R2 resistance is also here. The R4 is here on the numerator, also on the denominator. So you have to plug in the value of R4 or R2 multiple times if you're using a calculator. There is a simpler way to represent the same formula, which is this, where, for example, if you are thinking about this right-hand side term or the second term, what we are doing here is basically dividing the numerator and denominator with R4. So you divided the numerator with R4, you ended up with 1. You divide the denominator with R4, you get 1 plus R3 over R4. Similarly, you can do that same thing on the left-hand side. So the advantage here is that you have to plug in the values of R3 and R4 only once if you're calculating it with a calculator. And you can also use the first formula, there's nothing wrong with it, but this just makes it faster. Okay, one other interesting thing to note here is that in this particular problem that we just solved, that the signal path flows from left to right, correct? You have a voltage source on the left, and it flows to this R1, R2, R3, and R4 resistance. So the signal path is from left to right. And there are 2 resistors, R1 and R3, in series in the signal path. So you have R1 and R3. These are in series in the signal path. And that is the reason why you'll have 2 corresponding voltage terms in the gain expression. So as you see here, that we divided the overall gain expression into 2 corresponding voltage terms. Or you had one intermediate voltage, and you found out what is the ratio of the output voltage to the intermediate voltage, and then again intermediate voltage to the original source voltage. So this is also something very important, that if you had n number of series terms, so let's say you connected maybe 2 more resistances over here. Okay, so now you will have 3 resistances in the series path. In that case, you would have to represent the V naught over Vs as a combination of 3 different voltage terms or 3 different voltage ratios. So how many of these series terms will be there? There could be n different terms, maybe even thousands of terms. But you'll know that how many of those intermediate points will be there and how many of these voltage terms you'll have to multiply with each other to get the overall gain. So let's say, for example, I'm just giving out an example. It may or may not be applicable. But let's say in the exam, you have 4 different terms in series, 4 different resistances in series. So you know that you have to represent it as a ratio of 4 different voltages, and then you can solve it accordingly. That's another way of checking that you are doing it correctly. All right. Now, another thing that you might be asked. So for example, let's say right now, what we just did is that we tried to find out the voltage across R4. So we wanted to find out V naught, right? V naught is this point, which is the voltage drop across this R4 resistance. What if you are asked to find out the voltage drop across R3 resistance? And you are asked to find out the transfer function from the voltage drop across R3, so that is V3 divided by Vs. Let's say you are asked to find that out. So you can also do that in the same manner. So you can first find out what is your V3 over Vy, and V3 over Vy will be R3 divided by R3 plus R4. V0 over Vy was R4 divided by R3 plus R4. V0 over Vy, that was the voltage drop across R4 divided by this Vy, that was equal to R4 divided by R3 plus R4. Remember, because we are talking about voltage division, so the voltage will be proportional to the resistance across which we are taking the voltage. So V0 over Vy was proportional to R4, but V3 over Vy will be proportional to R3. Right? Makes sense? So if you are asked to find out the voltage gain and your output is taken across V3, this is the way you should proceed. You now find out V3 over Vy. You already know how to find out Vy over Vs, and then you multiply the two to get the overall V3 over Vs. So that's what we are doing here, that you already know V3 over Vy, and your voltage gain is V3 over Vs. So I'm denoting this in red just to make sure that we are looking at a different voltage now. So the voltage drop across this resistance, not the voltage drop across the R4 resistance. So you are trying to find out V3 over Vs. That would be Vy over Vs, which you already know from the previous example, and multiply that with V3 over Vy. So Vy gets cancelled, and you're left with V3 over Vs. And this will be your equation. Only difference is that this term will be R3 instead of R4.
Yeah.
All right, and that again, if you are solving that with a calculator, you can represent it in this form, where you only need to put in the values only once instead of putting them multiple times. For example, you had R3 in the denominator as well as in the numerator, but in this expression you have R3 only once, that is in the denominator. Let's look at an example of current gain. And any questions before this? All right. So in terms of current gains, we'll again use the same type of theory and same kind of formula. Just remember that when you are talking about current gain, the current through a resistance will be proportional to the other resistance, because current always takes the path of least resistance. So if you have a higher resistance, your currents will be lower. If you have a lower resistance, your currents will be higher. That's the intuition behind it, why the current will be proportional to the other resistance. So in this case, let's say you are asked to find out what is the current gain, that is I0 over Is. So Is is your input current source. I0 is the output current that is flowing through this resistance R4. And the network is exactly the same. You see the R1, R2, R3, and R4, that combination is still exactly the same. How to go about this? Again, you find out what is the equivalent resistance here. That's R3 in parallel with R4. You draw that R3 in parallel with R4 in the bottom figure. And note that now your I0 is hidden, because I0 is basically the current that is flowing through the R4 resistance. As soon as you combine R3 and R4 together, you lose information about I0, just like you had lost information about V0 in the previous example. Okay. So it's again the same concepts, but we're using them in case of a current division. So you represent this as R3 in parallel with R4. You have R2 in series. So in the next picture, what you are doing is basically you are representing this as R2 plus R3 in parallel with R4. And then you already had this R1 to ground. Okay. And let's denote this current flowing into this red branch as IY. Similar to what you had done before, you assume that the intermediate voltage was Vy. In this case, you are assuming the intermediate current as IY. Next, you can find out what is IY over IS, and that you can do from the theory of current divisions, right? Just like you did it for voltage division, now you're doing it for current division, and you use the formula for current division. So you see that IY over IS, that is the current flowing through this red branch, will be proportional to R1. It will be proportional to the other resistance, not the same resistance. So that's what we have over here. So that you can find out what is your IY over IS. And as the next step, as you have found out your IY, which is the current flowing here, you can represent that as the source, the intermediate source, and then find out the current division between R3 and R4. If you do that, you'll know what is your I naught. Right? Again, the same, it's just the dual of the previous problem. In the previous problem, we are looking into voltages. Now we are just looking into currents. That's it. So you can find out I naught over IY, which is basically R3 divided by R3 plus R4. Again, the current through R4 will be proportional to the other resistance, which is R3. So R3 divided by R3 plus R4, that's your current division when you are looking at a source of IY, the intermediate source, and then you are trying to find out what is your I naught. So again, in the same manner, you have I naught over IY. You already had IY over IS. You can find out what is your I naught over IS. That's just a multiplication of your IY over IS multiplied with I naught over IY. So again, exactly same as, or I should say the dual of what you had seen for voltage divisions. The overall current gain, now you can represent it as a function of all these resistances, just like you did it for the voltage division case. And again, the same theory applies that in the signal path from left to right, IS to I naught, there are two resistors, R1 and R3. So you had R1 and R3, which were connected in parallel in the current signal path. So there were two of these parallel paths, which was stealing away some amount of current to the ground. So this path was stealing some amount of current to the ground. The rest of the current was still flowing through the signal path. Again, this resistor was stealing away some amount of current to the ground. The rest of the current was flowing through the signal path. Because there are two of these parallel components which are stealing away the current, you will have two of these terms in the overall current expression. So in the voltage division case, we are looking into how many series elements were there, and your number of voltage division will be equal to the number of series elements you have. In this case, the number of current divisions will be equal to the number of parallel elements you have. Because if you, let's say you had another series resistance here, would the current be divided? No, right? Current does not get divided if there are two series elements. It will be the exactly same current flowing through both. Current will only get divided if you have a parallel element. So if you have something in parallel here, then some amount of current will be stolen by this parallel element, and then rest of the current will be flowing through the second series element. So you should look at the number of parallel elements that are present when you are looking into current division. So again, that's just the dual concept of the voltage division theory, where you are looking into the number of series elements, and the number of series elements will be equal to the number of voltage division. Here, the number of parallel elements will be equal to the number of current division. Okay? Any questions? So I think the rest of the problems in homework 1, they deal with this current division. Actually, problem number 3 deals with current division. 4 and 5 is related to amplifiers. So that's the next thing we'll be looking at. If there are no more questions, I would like to discuss about amplifiers next and how you can model amplifiers. So this is a model of a non-ideal amplifier. What is an ideal amplifier? An ideal amplifier looks like this: that you have an input, you have a gain of A, and you have an output. So let's say you have an input of V in, and you have a gain of A. Your output will be V out, which will be equal to A multiplied with V in. That's your ideal amplification. That you have an ideal amplifier, but your output is the gain of the amplifier multiplied with whatever you are putting at the input. Right? That is very easy to understand. That's the ideal case. But what we are showing here on the other side is a non-ideal amplifier. What does a non-ideal amplifier mean? That you'll look into op-amps in maybe in the next few lectures. But whenever we are looking into non-idealities in a circuit, the equations will not be as simple as this one, what I'm showing here on the right-hand side. So equations will be a little more complex. So what are the non-ideal components here in this particular example? what I had shown here as an amplifier, an ideal amplifier, which is V out equal to A multiplied with V in, that is basically this component over here. So this component says that the output voltage, so this is a this symbol means that this is a dependent voltage source. So independent voltage sources are represented as a circle. Dependent voltage sources are represented as a rhombus. Similarly, you can have dependent current sources and independent current sources. In this case, why is this a dependent voltage source? That's because the output voltage is dependent on the input voltage. Same as here, the output voltage is dependent on the input voltage. If the input voltage is small, output voltage will be small. If the input voltage is large, output voltage will also be large. So that's why the model of the ideal amplifier is just that dependent voltage source. So you have a V naught, which is basically your voltage gain in the ideal scenario, multiplied with VI. And where is this VI coming from? VI is basically the voltage developed across this resistance, which is the input resistance of an amplifier. So now we'll add one non-ideal component here. But I'm saying that the amplifier will have an input resistance of Rin. And yeah. So this amplifier has an input resistance of Rin. And that's possible to have, right? Because as you are setting a voltage here, you'll see that inside the amplifier there could be a large amount of resistance to ground, or when you look into frequency response, you'll see that there would always be some amount of parasitic capacitance in the amplifier, which will be creating some amount of input impedance. So for all practical purposes, we can right now assume that there could be an input resistance to the amplifier. We'll go into the distinction between resistances and impedances later. But right now, let's just assume that there could be an input resistance of the amplifier. And that comes because of non-ideality that, okay, you are putting some amount of voltage over here. So we expect that there is no path to ground from this voltage, but there could be a parasitic path to ground, which will mean that there would be a current flow to ground through this parasitic resistance. What does parasitic resistance mean? That again, it's a non-ideal resistance. It should not have been there in the ideal case. But because no device is ideal, no device is made with perfection, you'll see that there will be some amount of non-ideality. One of those non-idealities is this input resistance. We'll also look at input capacitance, but that will be later. Now, you have this input resistance over here. What does that mean? If you are applying a voltage source Vs at the input, that voltage source also has some amount of non-ideality. Any voltage source will have a equivalent series resistance associated with it. So an ideal voltage source is this, that you have you just have the voltage source Vs. That's an ideal voltage. A non-ideal voltage source is basically a resistance connected. And you know that the resistance will always be there. Let's say you are connecting a voltage source with any of your circuit in the lab. As soon as you're connecting with a wire, the wire has a resistance. Whenever you are making contacts, the contacts have a resistance. So even though this should not have been there in the ideal scenario, in all practical circuits, you'll always find there will be some amount of source resistance. Ideally, you try to make it as close as zero to as possible. So if it is smaller, it will be better, and we'll see why. So, and of course, because in the ideal scenario it is zero, of course, it needs to be very close to zero in the non-ideal scenario as well. Question, yes. Right. So, for example, if you are trying to analyze the circuit in a more simplistic way, you'll be doing it with an ideal voltage, right? But that analysis will not be correct because when you actually create that circuit on a breadboard or on a PCB, you'll see that things are different. This is just explaining why things are different. And one of the reasons that things will be different when you actually implement it on a breadboard or a PCB, this is one reason that the circuits will have, let's say, a non-ideal input resistance. The voltage source will have a non-ideal series resistance Rs. Both of them are non-idealities. Both of them should not have been there but it will always be there. You cannot avoid. So in ideal scenario, it will not be there, but ideal scenario does not exist in practice. If you are doing the circuit analysis for the first time, let's say this is your first circuit class, it's always good to start with the ideal scenario. And the ideal scenario is very simple. We already covered what amplifier is. We do not need to learn anything else if you are thinking about the ideal scenario. The only thing that you need to know is that there is an ideal voltage input, there is an ideal gain term, and there is output. And the output is equal to the gain multiplied with the ideal voltage input. That's it. That's all. Like you will see that analog circuit design or electronic circuit design mostly deals with amplifiers and filters. If we only think about idealities or only ideal terms, that's all there is. There's nothing else to learn. After this point, everything is non-ideal. Okay, so after this point in the class, even in this particular course and in the future courses that will be taking, you'll see that everything will be non-ideal because the ideal scenario is very simple. It's already done. Yeah. Questions?
Why does the non-ideal amplifier have a parallel resistance and the source have a series?
Very good question. So, for example, let's just assume that you had a. I'll start with the source. Let's just assume you have a parallel resistance. Will that have any effect? No, because the voltage at this point will still be Vs. Of course, you can say that, okay, there will be some effect that it will steal some amount of current. So the source will consume more power because there is some additional current going through that non-ideal resistance. But of course, there will be no effect on this voltage output. So if you're connecting this voltage to your amplifier, you'll still see this Vs in. The non-ideality will only be reflected in the voltage only if this is a series term. And the non-ideality in the amplifier is a parallel term, then you'll have a voltage division between this resistance and this resistance. And what will be available at the input of the amplifier is the voltage drop across this resistance. Right? So that's why it's defined like that. And even in practice, so when we go into the internal structure of the amplifier, which will be doing toward the later part of this semester, you'll see that this amplifier will be created using a BJT, a bipolar junction transistor, or a MOSFET, metal oxide semiconductor based field effect transistor. And there the input goes to, for example, a gate of a MOSFET. And right now you don't need to worry about this, what I'm drawing right now, but this is how a MOSFET symbol looks like. So the input goes to the gate. Ideally, there should not be any current flow here because you see that and these two things are disconnected. What it signifies is that there is a insulator oxide layer and there cannot be any current flow inside the gate. But what really happens in a MOSFET, and now we are talking about non-idealities and higher order non-idealities, is that any point will have some amount of capacitance. And that is true for anything. Even I have a capacitance to ground right now. I have a capacitance to the power lines. Every one of you have a capacitance to the ground and a capacitance to the power lines. And that's very interesting. So we were talking about the my research work, right? The human body communication. One of the major reasons that human body communication works is that you have these parasitic capacitances to ground and parasitic capacitances to the power lines. So that's always there. It's not only true for electronic circuits, it's true for us human beings as well. The table has a parasitic capacitance to ground. The computers have a parasitic capacitance to ground. So these are the non-idealities that I'm talking about. So the gate of the MOSFET will also have a parasitic capacitance to ground. So there will always be a parasitic capacitance to ground for this particular MOSFET. And then you can calculate what would be the impedance of a capacitance. So if you, I think some of you might already be aware of this, that the impedance of a capacitance is 1 over j omega c. And the impedance is basically, you can say that it's still a resistance, but it's the AC equivalent resistance of a capacitance. That's 1 over j omega c, where omega is the angular frequency. And c is the value of the capacitance. Now, this is the overall resistance that you have, right, at a particular frequency of omega. So, because of this parasitic capacitance, you have some amount of resistance or some amount of impedance at the gate. That's same as this resistance that we have just drawn here. And as you see that this is parallel to it because it connects it to ground. So that's why this is in parallel and that is in series. But very good questions. Okay, let's see. Do we have more time? Yeah, 5 more minutes. Okay, so we'll try to cover up the non-idealities that we are discussing right now. So one of the big non-idealities we just discussed is that the voltage source will have a series resistance and the amplifier will have a parallel input resistance. So of course, if you are applying Vs at the voltage source, you will not get Vs at the input of the amplifier. What would you get? If this is Rin and if this is Rs, you will get Rin divided by Rin plus Rs times Vs. That's the voltage you get at the input of the amplifier. That's the first non-ideality, the effect of the first non-ideality. And that's what we are showing here in the amplifier overall gain diagram. So you have Vs, you have Rs in series with the Vs. Then at the input of the amplifier, you had Rin. So the voltage will be divided between Rs and this Rin. And you will have the Vi, which is the voltage developed across Rin. The voltage developed across this Rin. The same voltage is this one. The voltage developed across Rin. That's the voltage you will amplify, not this voltage. Because this voltage is not even available to your amplifier. What is available to your amplifier is the divided voltage between these two resistors. So you will amplify that divided voltage. So V0 multiplied with Vi. And then let's look at the right hand side. On the right hand side, again, because as we said, that any voltage source will have a series resistance. Any voltage source will have a series resistance. And that's what we are showing here on the right hand. This voltage source has a series resistance R. And it will be true for, even if you don't want it, it will be there. So this voltage source has a series resistance of RO. And let's say the output of it, you're connecting it to a load resistance RL. So again, there would be a voltage division between RO and RL. So there would be a voltage division at the input side. There would be a voltage division at the output side. Those will be two major non-idealities that you'll be seeing for an amplifier. Question?
So, and then ideal part is zero.
Exactly. So ideal amplifier, the input resistance should not even have been there because this is in parallel. What is in the ideal scenario, if you assume that it is not there, what is this resistance? It's infinite. It's infinitely large, and then only you'll say that it's not there. It's open circuit. Right? So ideally, this input resistance is infinite for an ideal amplifier. The output resistance for an ideal amplifier is 0 because that's in series. If it is not present, you will not have any resistance in series. So the output resistance in an ideal scenario is 0. The input resistance in an ideal scenario is infinite. Okay, now taking into consideration that you have these two voltage division at the input and output as well, what is the overall voltage gain of the amplifier? The overall voltage gain of the amplifier, that is, let's say this V out divided by Vs, that would be Vi over Vs, that's a voltage division between Vi and Vs, okay, multiplied with V2 over Vi. So the amplification between V2 and Vi, so that's your second term. And the third term is the voltage division ratio of V0 and V2. So V0 over V2. So as you see that these are multiplication of 3 different gain terms for the non-ideal amplifier. Your homework question number 4 and 5 deals with this kind of a non-ideal amplifier and what would be the voltage gain for this non-ideal amplifier considering the voltage division at the input, the voltage gain in the amplifier, and the voltage division at the output side. And here we are just representing the voltage division at the input and output as a ratio of resistances that you have already learned in this class. So we'll stop here. In the next lecture, we'll start with Thevenin and Norton's theorems. But in the meantime, also look at the homework and let me know if you have any questions.